Should we just go ahead? So it's my great pleasure to introduce Ben Schmidt of Michigan State, talking on Preserve One, Preserve All.
Okay, thank you. Let's see if I can get my screen to advance. Okay, yes, thank you, organizers, Carolyn, Ramiro, and Emilio. And while I have an audience here, I'd like to plug a job that we're going to have at Michigan State University, I hope, that will be running next fall, a search for a geometry search. So if you know anyone who's interested, please send them our way. Okay, so the setup for today's talk, we'll start with two metric spaces, x and y, and just a function f between them. And a priori, this function has no regularity properties. It may not even be continuous. We know what it means for the function to be isometric. That it's isometric if for each pair of points in x, the image pair of points in y make an equal distance. If in addition, f is isometric and surjective, then we say it's an isometry, and isometries have an isometric inverse. And they're continuous. Here's the motivating question for today. Are there proper subsets of the Cartesian product of x that can already certify f as isometric? In particular, does a level set of the distance function from x cross x to r certify, can a level set certify that f is isometric? So by level set, I just mean those pairs of points in x that have a fixed distance r, and I'll denote it by x sub r. So that motivating question gets to this following definition of preserved and strongly preserved distances. We'll say a distance r, first of all, note these are all positive real numbers. So a positive real number is preserved by the function f if the level set is non-empty. And if in addition, whenever a pair of points a and b and x have distance r, so too do the image points f of a and f of b in y. And a positive real number is a strongly preserved distance for f if it's a preserved distance, and if in addition, anytime you have a pair of image points making distance r and y, they come only from pairs of points in x that make distance r. Okay, so here's the first motivating theorem for today. It's due to Beckman and Quarles, and they published it in 1953. And it states that if x and y are both Euclidean space of dimension 2 or higher, then as soon as a function preserves a single distance, it's necessarily an isometry. It must preserve every distance. So if you preserve one distance, you preserve all distances. I learned about this in 2017 at the Lead Group Actions in Riemannian Geometry Conference at Dartmouth College that Carolyn Gordon organized. And I learned about this from Dmitro Yeroshkin, whose name I see over there on my screen. He shared the case d equals 2 with me as a puzzle one evening. Later, I shared it with a student at Michigan State University, Rodrigo Matos, who recognized it as a 1997 Brazilian Olympiad problem. And I thought about this for a little while. I thought about the case of d equals 2 in Euclidean space, and then eventually realized that any higher dimension works as well, and then things work as well in hyperbolic space. And I thought, oh, that's interesting. You know, maybe I should write a short paper. Only later to realize that this was the Beckman and Quarles theorem, which I happened upon just by accident searching Google. Okay, so what about dimension 1? Why must the dimension be 2 or higher in the statement of Beckman-Quarles theorem? Here's a function from the line to the line, a bijection that fixes every rational number and shifts every irrational number 1 unit to the right. It's discontinuous, and so not an isometry. On the other hand, every positive rational number is strongly preserved by the function f. You can also cook up continuous functions of the line to itself that preserve a distance but are not isometries. There's a problem often credited to Alexandrov, although I think he was working specifically in the context of Banach spaces, but namely, which metric spaces X have this preserve one, preserve all property? That given any function from X to X, as soon as one distance is preserved, every distance is preserved. So perhaps the next most simple example to consider after Euclidean spaces are the Euclidean spheres. So consider the unit sphere in Euclidean n+1 space equipped with the standard metric where the distance between a pair of vectors is the angle that they subtend. And here's a bijection. So take a pair of poles indicated in the figure by the purple and yellow dot. And the bijection under consideration here interchanges those two poles while fixing all other points. Again, this is discontinuous and so not an isometry. But on the other hand, if you take any pair of vectors making a right angle, then the image pair of vectors also make a right angle, as well as any pair of vectors making a straight angle, the image pair also makes a straight angle. That's to say that pi over 2 and pi are both strongly preserved by this bijection. So spheres do not have the preserve one, preserve all property. Which leads us to the second motivating theorem for today's talk, proved by Everling and published in 1995. He proved that if x and y are both the sphere of dimension 2 or higher, then as soon as a function preserves a distance less than pi over 2, it's necessarily an isometry. Okay, and that brings me to joint work with Meera Mainkar from Central Michigan University. These two model geometries, Euclidean spaces and spherical spaces, are Riemannian manifolds, perhaps the simplest examples. And we were wondering, is there a common Riemannian geometry generalization of the two motivating theorems? So after some work and thinking about this for a while, we came to the following conjecture. Let X be a complete Riemannian manifold with dimension 2 or higher and having positive convexity radius. I'll say a few words about what the convexity radius is in a moment. For now, let me just say that if X is a closed manifold or covers a closed Riemannian manifold, then it has a positive convexity radius. Okay, then for each function f from x to x, as soon as the function preserves a distance less than the convexity radius, it's necessarily an isometry. Okay, so before moving on to discuss the convexity radius, let me just mention that for the sphere, the convexity radius equals pi over 2. Okay, a few words about the convexity radius. There's many notions of convexity in Riemannian geometry. This one is strong convexity. So a subset C of the manifold X is strongly convex. Whenever you take a pair of points in C, there's a unique minimizing geodesic in X, having those endpoints C1 and C2. And moreover, this unique minimizing geodesic stays inside the subset C. In a paper published in 1932, Whitehead showed that metric balls of sufficiently small radii are strongly convex. Now, how sufficiently small the radius must be depends on the center of that metric ball. And the convexity radius is the supremum of non-negative real numbers R, such that for every S lying between 0 and R, every metric S ball in X is strongly convex, independent of the center point. It's related to more familiar geometric radii. It's the minimum of half the injectivity radius and the focal radius of X. Okay, so there's the statement of the conjecture again. We have a complete manifold of dimension 2 or higher, having positive convexity radius. Then, given any function from X to X, having a preserved distance less than this convexity radius implies that F is an isometry. Okay, so let me say some prior supporting results. First is the case of the Beckman and Quarles theorem. I'll just mention here that the convexity radius of Euclidean space is infinity. The case of hyperbolic spaces was handled by Schmidt in 1979, and hyperbolic spaces also have infinite convexity radius. Everling's theorem concerning spheres. As I mentioned earlier, the convexity radius of a sphere, unit sphere, is pi over 2. So these are the model geometries, constant curvature spaces. So besides those, there were papers of Berezovsky and Andreev that analyzed Hadamard manifolds, simply connected manifolds of non-positive sectional curvature, and they showed that a bijection of such a space with a strongly preserved distance is an isometry, and these spaces have infinite convexity radius. Okay. In 4, the case of Hadamard manifolds, their arguments very much do rely on the non-positive curvature. On the other hand, many of the arguments in non-positive curvature are convexity type arguments. So based on that, it's not unreasonable to expect that there's some generalization that involves convexity radius. Okay, so any questions so far before I move on? All right.
So nobody has looked into, say, symmetric space crosses or things like that?
Not before we came to this, not to my knowledge. We couldn't find anything. We've looked at compact rank 1 symmetric spaces.
All right.
So here's our new supporting theorems. In our theorems, X will always be in the conjecture, as in the conjecture, so of dimension 2 or higher and complete. And then for the function from X to X, we'll always assume that it's either surjective or continuous, requisite properties for it to be an isometry. So here's our first theorem. This is the most general theorem in terms of the space allowed. So here X is just as in the conjecture. And we assume that there are 2 preserved distances, not just 1, but 2 below the convexity radius, strongly preserved distances with an irrational ratio, and then deduce that F is an isometry in this case. Okay, in our second supporting theorem, X is a 2-point homogeneous space, so much more specialized class of spaces. And we show if there's a single strongly preserved distance below 2/3 the convexity radius, then F is an isometry. This 2/3 is unfortunately just a byproduct of our method of proof. The 2-point homogeneous spaces, I think this crowd probably knows well, but they're the spaces for which the isometry group acts transitively on the level sets of the metric. They were classified in 1952 by Wang, and the classification was simplified in 1991 by Javo. Here's the spaces. So in the first box, you have the non-compact 2-point homogeneous spaces. These are all Hadamard manifolds and have infinite convexity radius. In the second box, you have the compact rank 1 symmetric spaces. And for these, the convexity radius is half the diameter. Our proof of the theorem 2 is not case by case. We don't analyze each of these spaces individually. Rather, it uses just the definition above. Okay, and then the third supporting theorem concerns X with having all geodesics closed. So suppose you have X with a one periodic geodesic flow. Then each strongly preserved distance below the convexity radius is rational, or if there's a single irrational one, then F is an isometry. Right. These 2-point homogeneous spaces, these compact rank 1 symmetric spaces all have one periodic geodesic flow after rescaling the metric. So there's overlap with the second theorem.
Ben?
Yes.
Ben?
Yes.
Hi. Can you please recall the definition of strongly preserved, unpreserved distance?
Oh, sure. Who's that question from? I didn't see. Well, in any case, I can go back.
I was late, sorry.
Oh, I'm sorry. Let me go back some slides.
No, just the definition of strongly
Okay.
preserved distance and preserved
I'll
distance.
go back.
No, but
Sure. Yeah,
you
my
don't have
hands are off. Computer's still going. So I'll just say it. They're all positive numbers. A positive number R is preserved by the function. If whenever A and B have distance R and X, then F of A and F of B have distance R and Y. And R is strongly preserved if you replace the implication with an if and only if implication.
okay. Okay. Thanks. Sorry.
Sure, no problem. Let's see, where did I get? Oh, right. I was going to say that in addition to the compact rank 1 symmetric spaces, it's known that smooth spheres also have Riemannian metrics with periodic geodesic flows that are not the standard symmetric metric. Okay, so each of these three theorems, there's a common strategy to all of them. And strategies, well, to start with one preserved distance and use that to produce new and smaller preserved distances, and then apply what we call the immersion theorem. So for the immersion theorem, it states that you have a complete Riemannian manifold X of dimension 2 or higher, an arbitrary Riemannian manifold Y. F's a function from X to Y, and we assume that 0 is a limit point of the set of preserved distances. So in other words, there's a arbitrarily small distances that are preserved. And then the conclusion is that under this assumption, F is a smooth map, and moreover, it's a Riemannian immersion. This immersion theorem generalizes the Myers-Steenrod theorem, where they showed that if you take X and Y to be equidimensional, and if you have a function between them that preserves the distance function, so every level set of the distance function, then it's necessarily smooth and is a Riemannian isometry. Our proof follows a proof of Pillai of the Myers-Steenrod theorem pretty closely. So it's an adaptation of a known result. Oh, it looks like there's a question in the chat. Let me see. Am I right that most of your examples are Riemannian manifolds of positive sectional curvature, or is it just accidental? Thank you for your question. The examples I mentioned earlier include manifolds of both positive and negative sectional curvature. And also the theorems I stated, like the first theorem, pertains to manifolds with variable sectional curvatures. So it's independent of sectional curvatures. Okay, any further questions? All right, thank you. Okay, so we have a strategy for proving that a function that preserves a distance, a single distance, is an isometry, and that's to find, starting with that first distance which is preserved, to find new, smaller preserved distances converging to zero. But it begs the question, how do you actually produce new and smaller preserved distances? So let me start with new distances and just give an example with the Euclidean plane, the case of the puzzle. So suppose you have a function from the plane to itself, and that one is a preserved distance. Then let's see that root 3 is also a preserved distance. As a preliminary claim, let's see that if you take a pair of points, W and Z, having distance root 3, then the image pair of points has distance 0 or root 3. So you can argue with this picture. There's the points W and Z lying at distance root 3. And in the Euclidean plane, you can arrange those to be vertices of two equilateral triangles having side lengths 1 that share a common edge, X and Y. So there's a pair of points X and Y is in the figure. Okay, well, 1 is a preserved distance. So pairs of points that have distance 1 map to pairs of points having distance 1. So that leaves for two possibilities for the images of the vertices of this hinge. I think of this as a hinge that can fold along the edge X, Y. Now, we know nothing what the map does on the edges or in the interior of this hinge, but we know what it does on the vertices. And there's two possibilities indicated by these figures. One is that the hinge maps to an open hinge, in which case the image points f of W and f of Z still have distance root 3. And the alternative is that the hinge closes up, which is the case where the image points agree. Okay, so that's the preliminary claim. Now let's see that root 3 is actually preserved. So take an arbitrary pair of points, A and B, having distance root 3 apart. Here they are in the figure. There's B in the circle centered at A, having radius root 3. And by the previous claim, the image pair, f of A and f of B, have distance root 3 or coincide. It's recorded as letter A there in the red box. So now choose a point C, which also lies in the blue circle, and the circle centered at B of radius 1. Since C lies in the circle of radius root 3 centered at A, the previous claim applies to the pair A and C. And so the image pair f of A and f of C have distance root 3 or also coincide. Now, I'd like to argue that f of A and f of B have distance root 3, and we'll argue by contradiction. So assume not. Then we'll obtain a contradiction in the following sequence of equalities. First, B and C have distance 1 apart by construction. One's a preserved distance, so too do f of B and f of C. But if f of A and f of B do not have distance root 3, then by A, f of A and f of B are equal. And so that substitution is made here. But now we look at the distance between f of A and f of C. And if you look at B, the alternative is that they have distance root 3 or 0. They can't have distance 1. So this leads to a contradiction to B. Okay, so that concludes the proof that if 1 is a preserved distance in the plane, then so too is root 3. Okay, how do you actually get a smaller distance? Root 3 is bigger than 1. There's many ways to do this. And there's many papers written about the different ways. Here's one such way. So assume that the function f from the plane to itself preserves both 1 and root 3, and let's show that 1/2 is a preserved distance. Here's a sketch. I claim that if you take a set of points congruent to the integers in the plane, that set of points will map to a congruent set. Well, here's my set of points congruent to the integers. And I can arrange these equilateral triangles as in the picture. And since root 3 is a preserved distance, these hinges all map to open hinges. That's the idea to prove that a set congruent to Z maps to a set congruent to Z. In particular, 2 is a preserved distance as well as 1. And so if you take a set of points congruent to the vertices in this isosceles triangle having long edge lengths 2 and short edge length 1, the indicated vertices will map to a congruent set as well. So this distance here is 1/2, and that is now a preserved distance. Okay. All right, success. So that's the case for the Euclidean space, and you can iterate this to get arbitrarily small preserved distance and apply our immersion theorem, or you can just use a more straightforward argument for the case of the plane to conclude the Beckman and Quarles theorem in dimension 2. Now, this approach works well in the other model spaces, Euclidean spaces of dimension 2 and higher, and same with the hyperbolic and spherical cases. And what underlies that is that in these model spaces, there's a unique regular simplex up to isometry. There's a unique simplex having all equal edge lengths up to isometry. So for an arbitrary Riemannian manifold, that's not true. And I'd like to try to now indicate what role Meera and I think convexity plays in the conjecture. So to do that, let me introduce some notation. Given a point X in the space and a positive real number, let D sub X R denote the closed metric ball of radius R, or the metric disk of radius R with center X. And SXR, its sphere boundary. Now, we use the fact that two circles intersected in the earlier proof. That's where it came up. Choose this point C in these two circles. So I needed to know that those two circles intersected. Okay, so we prove an analog, or we give a criterion for when two metric spheres intersect using the convexity radius. And we call this the metric sphere intersection theorem. So to state it, take a pair of points in your space X and two positive real numbers below the convexity radius. And the first statement says that the two metric spheres with center X1 and radius R1 and center X2 and radius R2 intersect, have non-empty intersection, if and only if the indicated inequalities hold for the distance between X1 and X2. The implication in purple there is just an application of the triangle inequality. You take the points X1, X2, and a point C in their intersection, and then write down all possible, I guess, 3 different triangle inequalities you can write, and from those you can deduce the inequalities. The implication indicated by the purple now can fail when the radii are equal to the convexity radius or larger. And here's an example. So here's the unit sphere again. X1 and X2 are supposed to be antipodal points here. So this distance D is pi. And we take both radii to be 3 pi over 4, which is larger than the convexity radius pi over 2. And so these inequalities hold. On the other hand, you can see from the figure that the metric spheres have no point in common. Okay. And then part B of this theorem is to understand the equality cases of the inequalities. And when one of the equalities holds, that's equivalent to the two spheres having a single point of intersection in common. You might wonder why I had to put that R1 minus R2 is positive. It's not strictly speaking the equality case here, and it's just because if they're equal to 0, then these spheres are the same sphere and they'll have more than one point in common. Again, and this implication indicated fails or can fail when the radii are equal to the convexity radius or larger. Here is an example again in the unit sphere. I take again a pair of antipodal points, so this distance d is pi. You take both R1 and R2 to be equal to pi over 2, the convexity radius, and then the metric spheres coincide and so have more than one point. Okay, so this is not a super difficult theorem to prove, but turned out to be useful in this context of studying the preserve one, preserve all property. And so, having said that, let me give some heuristics for the first theorem. Here's the statement again, just to remind you. We have X dimension 2 or higher and complete. F is surjective or continuous, and we're assuming that there's two strongly preserved distances below the convexity radius having irrational ratio. We'd like to argue that F is an isometry. Okay, so the first thing we prove is just having a single strongly preserved distance lying below the convexity radius implies that the function itself is injective. The functions are injective and also surjective, which is one of the standing hypotheses, then it's bijective. Or if the function f is injective and also continuous, one can apply the invariance of domain. And so in either case, we assume that f is bijective. So we conclude f is bijective, sorry. Once you know the function's bijective, it will carry metric spheres having a preserved radius to a metric sphere having a preserved radius bijectively, and also preserves the intersections between such metric spheres. There's that statement in symbols. In particular, it's going to preserve the property that two spheres have a single point of intersection in common, which characterizes sums of numbers and difference of numbers by the sphere intersection theorem. So from this, we're able to conclude that if you have two strongly preserved distances below the convexity radius, and a pair of points x1 and x2 whose distance is either their sum or their difference, then the image pair also have a distance which is either the sum of those two numbers or the difference between those two. Then with a bit more work, we can show that, in fact, if you take a pair of strongly preserved distances below the convexity radius, then their sum is also a strongly preserved distance, and so too is their difference. We think of this as being a group structure on the set of strongly preserved distances that lie below the convexity radius, closed under addition and subtraction. So that's where this hypothesis that you have two group elements making an irrational ratio is useful, which allows us to conclude that 0 is a limit point of the preserved distances of F, and then apply the immersion theorem to conclude that F is an isometry. Okay, so that's the basic structure of the proof of the first theorem, omitting some details. The same line of reasoning applies mostly in the case of theorem 2. This is the case for the 2-point homogeneous spaces. Up to the last step, we don't have this additional distance with a rational ratio to use. We only have one preserved distance a priori. So to get a second preserved distance, we prove another convexity theorem, which we call the diameter intersection theorem. And to just state this theorem in words, it states something very believable, that if you move two convex disks apart, then the diameter of their intersection decreases as you move them apart. Now, to make this precise, take a R below the convexity radius and an arc length parametrized geodesic of length 2R. And we're going to look at the intersection of two closed disks of radius R, one which is held fixed with center gamma of 0, and the other which is moving away from gamma of 0 along the geodesic, so one centered at gamma of t. And we could look at their diameter of the intersection of these two and think of that as a function of t between 0 and 2R. Here's a figure to indicate the function g. Okay, and so the statement is not particularly surprising. This function is continuous, strictly decreasing from 2R, the diameter of the disk of radius r, down to 0. And moreover, if you take one of the center points to lie on the circle of the other one, then the diameter is strictly bigger than r. So g of r is bigger than r. We actually prove this in more generality. So we have a statement where the two disks don't actually have to have equal radii, but just both have a radius lying below the convexity radius. And there's an analog in that setting, but this is good enough for the application here. And I'll just mention that in the model constant curvature spaces, this G has better regularity. You can show it's smooth. It's actually concave down. Okay, but we couldn't establish better regularity up to now in the general setting. Let me just point out that, again, this is using the convexity radius assumption that R is bigger. It can fail if R is bigger than or equal to the convexity radius. So here's yet another example using the sphere. Take R to be pi over 2 equal to the convexity radius of the sphere. For any point in the sphere, the disk of radius pi over 2 has boundary of great circle. Any two great circles in the sphere intersect in a pair of antipodes, so a set of diameter pi. And so this function is constant equal to pi, so not decreasing. Okay, so how do we apply this? So this function g is continuous, strictly decreasing from 2r to 0, and g of r is bigger than r. So if you want to know when g of r equals to r, it has to happen at some time parameter t naught that lies strictly between r and 2r. Now, what time t naught does this happen? Well, that really depends on the geodesic. The whole statement of the theorem is about a geodesic of length 2r. So the time at which these two disks intersect in a set of diameter r depends on the geodesic, but not in a 2-point homogeneous space, because in a 2-point homogeneous space, any geodesic of length 2r can can be mapped to any other geodesic of length 2r via an isometry. So here's the corollary. There's a unique T0 between r and 2r for a 2-point homogeneous space, so that you can characterize the distance T0 in terms of the two r disks having an intersection with diameter equal to r. In the plane, this T0 is √3, which we've seen before earlier. So here's a corollary. If X is 2-point homogeneous and R is less than 2/3 the convexity radius, I'll say a word about this 2/3 in just a minute. And when R is strongly preserved, so too is T0. And then by the group structure property, so too is T0 minus R. But since T0 lies between R and 2R, this number T0 minus R is strictly less than R. So we go from a preserved distance R to a strictly smaller preserved distance T0 minus R. And then this procedure can be iterated to get 0 as a limit point. Now, why the 2/3 here? It's in the highlighted implication. We know R is a preserved distance. And so disks of radius R, well, we know the distance R is preserved. We'd like to say that disks of radius R are preserved, as are sets of diameter equal to R. And to do that, you have to first show that if you have a pair of points having distance less than R, then so too do the image points. And so to make that argument, we had to reduce this number to 2/3. I won't go into more details there. So that's the outline for the second theorem. Now for the third theorem, the case where the geodesic flow is one periodic, we apply Kronecker's theorem. And so if you remember back the picture I had where I was trying to show in the Euclidean plane that a set congruent to the integers maps to a congruent set. Well, another way to interpret what I was saying is that if you take a geodesic in the space and a set of equally spaced points along that geodesic, where the spacing between successive points is the preserved distance, then that will map into a set of equally spaced points in a geodesic. Okay. And that's exactly the setup we need to apply Kronecker's theorem, that an irrational rotation of the circle has dense orbit. And that's how we construct smaller preserved distances in theorem 3. Let's see how I'm doing on time. Oh, I forgot to set my timer. Let me just conclude by saying some future directions. I hope I'm not over time. First is to try to verify this conjecture for closed manifolds having a chaotic geodesic flow. The idea here is to use smooth methods. Everything I'd mentioned, the work with Meera so far was using just methods of geodesic metric spaces. So by chaotic geodesic flow, I mean transitive and having periodic orbits dense. Transitive means that there's at least one dense orbit. These manifolds include manifolds with negative sectional curvatures, or more generally manifolds with anossive geodesic flows, and more generally manifolds with expansive geodesic flows and no conjugate points. Separately, rank 1 manifolds with no focal points, higher genus surfaces with no focal points, and more generally those with no conjugate points. So these are well-known examples of manifolds having chaotic geodesic flow. Here's a sample theorem. So assume you have 2 equidimensional closed manifolds, both having injectivity radius larger than 2, and a C3 diffeomorphism between them that preserves the distance 1. Then if M belongs to one of these first 6 classes, and if the target N belongs to one of the first 5 classes, then F is necessarily a smooth Riemannian isometry. And I won't go into too many details here, but the idea is we show that the geodesic flows are equivalent. And then from there, we're able to bootstrap that using well-known properties of the geodesic flows for these particular classes of spaces. So yeah, we have two preprints for the stuff I've discussed so far. We're writing one for this, and we'll get it out sometime, hopefully not too long from now. Here's a different direction. Suppose the convexity radius of X is larger than 1. Okay, well then we'd like to know that each function which preserves 1 is an isometry. And so the group of such things ought to be a Lie group. And that's because the isometry group of a Riemannian manifold is a Lie group. Now, so this was proved by Myers and Steenrod for the isometry group is the same whether you think of it in terms of the distance function or the Riemannian metric, and it's a Lie group. An important part of that argument is using the fact that isometries of Riemannian manifolds are determined by their value and their derivative at a single point, which gives you a way to map the group into the frame bundle. Okay, so we have an analog of that for diffeomorphisms that preserve 1. Namely, if you have 2 such with equal value and equal derivative at a point P, then they're necessarily the same. So for instance, if a diffeomorphism preserves the distance 1 and has a fixed point and derivative identity at that fixed point, then it's necessarily globally the identity map. Here's a different direction. So we've been considering mostly functions that preserve a distance between equidimensional manifolds, except in the immersion theorem. So what happens if you allow the dimensions to differ? So concretely, suppose you have a function from the plane to 3 space that preserves 1, then must it be the natural inclusion of the plane into 3 space? We don't have an answer even when we know F is a smooth embedding, even if you want to assume that. But as a caution, I should mention that you can't increase the dimension from 2 to too much higher, because there is a function from the plane to 6-dimensional Euclidean space that preserves the distance 1. So it carries each point of the plane at distance 1 to pairs of points in 6 space having distance 1 apart. And this function has image consisting of exactly 7 points, and so isn't continuous. Construction of such a function uses that the chromatic number of the plane is at most 7. And you can kind of, the kind of reasoning that goes behind the existence of such a function F also proves that if you take any closed manifold or any Riemannian manifold covering a closed manifold, it admits a function to a sufficiently high dimensional Euclidean space that preserves a single distance, but will have a finite image set. And then I didn't say anything about group actions. I know this is a group actions seminar, so this was my attempt to try to say something about that. So suppose that the convexity radius is bigger than 1, which can be arranged by rescaling. And assume that a compact Lie group acts on X and each element acting preserves the same common distance 1, then must the action be by isometries. And the thought here is, well, we don't know how to prove our conjecture for a single function F, but maybe it's easier if you have a group of such functions acting on a manifold X, each of which preserves the common distance. So I haven't really thought about this for yet. I just thought to write it on the slide for this talk today. Okay, and that's all I have prepared for today. Thank you very much.
Thank you for a really fun talk. Are there questions? I was curious about some of those things you said you'd done at the end, like the fact that if you just preserve the sphere at one point, is that right? And your differential is the identity at that point, that it's already the identity verbally. Is that easy or is that hard?
It's not very hard once you have the yeah, it's not very hard. I'm trying to remember the exact argument. We had to write a one linear algebra statement. So it's yeah, I'm sorry, I don't remember our exact reasoning, but I'm happy to see where we wrote it down if you want to see. But it's not particularly hard. There was
Are there other questions or? If not, thank you again. It was really interesting. I just think that's, I'm always so fascinated by that. I just think it's such an interesting project and so neat that you can